Hello. In the last class, in the last lecture, I have reviewed the hypothesis testing, the general framework of hypothesis testing, and let me start from here. I have done this briefly at the end of the last lecture. Let me do it again. And what's important to understand the framework is that there are three different betas. By the way, the model we are interested in is something like this. So y, the left-hand side variable, is the test score, and x is the student-to-teacher ratio, and then beta 1, which is our main parameter of interest. The beta 1 captures the effect of student-to-teacher ratio on the test score. So we would like to carry out some hypothesis test for a hypothesis about beta 1 in this case. Anyhow, but under the same beta, beta can be interpreted in different ways, and there are three different betas in our analysis. First, the first value of beta is what you believe in your hypothesis. So in my hypothesis, I believe that say lowering the student-to-teacher ratio by 1 unit will increase the test score by say 2 points. So then beta will be -2 in my hypothesis. That is just a belief. It's an assumption, and it has nothing to do with the data. So it is your belief, and I would like to check if my hypothesis is consistent with the data. And the second aspect of beta is an estimator. So it is simply calculated from the data. We learned how to estimate the parameter from the data, and beta hat is a notation for that, and it is the OLS estimator. And the third beta is the true value of beta, but it is unknown. We know that there exists the truth, but no one knows what is the true value. So it is just a conceptual, purely theoretical object, and beta star is the true value of beta, and it is unknown. But we don't know what is. So later you can calculate beta hat, and beta 0 is your belief. So you can choose your own beta 0, but beta star has no specific value at all because it is unknown. It is never known. Then what's the relationship between them? First, the difference between estimator beta and the true beta is the estimation error, right? So and it is known, so estimation error does exist. It always exists, and even though error can be any value, but its distribution. So how the estimation error is distributed with what kind of probability distribution. So it is kind of under control. And the difference between your belief and the true value is it captures whether your hypothesis is wrong or not. So if they are the same, if the difference is 0, that means your hypothesis is correct. But otherwise, if the difference is non-zero, then your hypothesis is wrong. So, however, the problem here is because even though beta 0 is your belief, but beta star is never known, and we never know whether it is 0 or not. So it is never known. So when you compare these two differences, the first guy is is rather easier to handle. And anyhow, we don't know beta star, so what we can rely on is the difference between the estimator from the data and the value implied by the hypothesis. So the difference between these two guys can be either they may be from the estimation error or from the wrong hypothesis. Somewhere, some of like it arises from one of the two reasons or some kind of in the middle of them, a mixture of them. And then how can we handle that problem? If we knew that, like I told you that the estimation error is the distribution is known. So how is it known? If you use the true value, if the true beta was available, it is not, but if it was available, then beta hat minus beta star is the estimation error. And if you standardize the estimation error by the standard error of the estimator, right? Standard error of beta hat. If you divide it by this standard error, then this standardized estimation error is approximately standard normal distribution, which is really nice. It is implied by the central limit theorem. And what's good about this is beta hat is calculated from the data. Standard error is also calculated from the data. So they are calculated by Stata. Stata calculate them for you. And by the way, the problem here is we cannot calculate this because beta star is never observed. So we are going to make a trick. Anyhow, what we want to do here is we would like to compare this. This is what we are interested in, the difference between the estimator and your hypothesis, and assume that your hypothesis is correct. So what you believe is the truth. And if you assume that, then the numerator can be simply replaced with the difference between the estimator and the hypothesis, which is still normal distribution because they are the same thing. So then usually this standardized, it is the, so you can interpret this guy as the standardized difference between the estimator and the hypothesis. So you would like to see how different what you believe and what you observe. And that standardized difference is referred to as the t statistic. So usually it is denoted as t. So this t statistic is approximately normal distribution following from this result, right? And you must have heard about the t statistic. And then the idea is, as I said, basically what we are doing here is we are comparing whether it's how different what you believe and what you see, and if they are close, if they are similar to each other, that means, oh, your hypothesis is good. Your hypothesis is consistent with what you observe, so it's likely to be correct. Your hypothesis is likely to be correct, maybe correct, but if the difference is too large, then you need to think about this. Then the difference, as I said, the difference could be coming from one of the two reasons or both of them, mixture of them. Anyhow, the possible reasons why there is such a big difference is that could be because of the estimation error, or that could be because of wrong hypothesis. Just hypothesis is wrong, or estimation error is you are just unlucky to get large errors. But then anyhow, we are going, so then intuitively, like you know how the estimation errors are distributed, and that means if it is too large, you can calculate how unlikely it is unlikely to happen such a large estimation error occurs. So if you think it's too unlikely, then you have to think about the other reason. So if such a large estimation error is unlikely, then the reason for this large difference is the wrong hypothesis. Then you conclude that the hypothesis is wrong. And in this rationale, the likelihood is measured by the p-value. So p-value captures how unlikely such a large estimation error can occur. So if the p-value is close to 0%, that means the difference is too large. If the difference becomes larger, the p-value converges to 0. So if the p-value is too small, that means such a large estimation errors are unlikely to happen. So it's more likely to be the wrong hypothesis. So the reason for this large error could be due to the wrong hypothesis. That is the rationale. And then how do you, formally, how do you make the decision? We set the significance level, probability 1, 5, or 10. Usually these three probabilities are the most common probabilities, and 5% is the standard. So in this course, I guess if I don't say anything, it is always 5%. So and maybe we are only considering 5% in this course, but when needed, you may change it to 10 or 1%. Anyhow, so when you have 5%, that means if the likelihood of the large error is lower than 5%, then I am going to reject the null hypothesis. So the rejection rule is something like this: reject the null hypothesis if the calculated p-value is smaller than the significance level. So very easy to make the decision. Alternatively, you may use the t-statistic directly. So if the difference is too large, you are going to reject. So then the difference is standardized into the t-statistic, and the decision rule based on the t-statistic depends on whether you are using two-sided or one-sided alternative. And maybe in this course, I'm going to consider two-sided test only. But when needed, you need to change the t-stat, and p-value need be recalculated, and t-stat itself does not change, but the rejection rule changes. So anyhow, if you assume two-sided test, then we are going to reject the null hypothesis if the t-statistic is outside of those intervals. Plus minus 1.96 is the standard level. Approximately the rule of thumb is 2. So plus minus 2. So if the standardized difference is within plus minus 2, then I think that the difference is not that large. But if the standardized difference, which is the t-statistic, if the standardized difference is larger than plus minus 2, approximately 2, then that's too large. So you are going to reject the null hypothesis. Okay, so I have reviewed the general framework for the hypothesis testing, and we are going to use this in the regression setup. See you in the next video. Bye.